Hello everyone, this is José María Martín Olaya speaking. I am professor at the Faculty of Physics in the University of Seville in Spain. Thank you for watching this screencast featuring this manuscript recently released in Scientific Reports. It is a piece on human sleep ecology, a roadmap describing when we get to bed or when we rise up, with less emphasis on how much we sleep, an interesting concern nonetheless. The manuscript analyzes a rather eclectic cross-cultural collection of sources. First, 8 industrialized countries, 6 in Europe, 2 in America, all of them in the extratropical region. And second, 7 previous reports in 9 pre-industrial societies in the subtropic. Every of these reports consider at least one society without access to electricity. In some cases, that is paired with a neighboring location with access to electricity. They provide some clues on what we know as natural sleep, the sleep timing before the advent of cheap, efficient artificial light. The paper puts emphasis on the cycle of light and dark, which dominates our circadian system, and on seasonal adaptation, which is influenced by latitude. The important thing is that unless you live at the subtropic, this equinoctial setting is pretty much altered by seasons and latitude. The task is then revealing sources of synchronization of the human sleep-wake cycle in relation to the light-dark cycle. To provide some context, 1 year ago Scientific Reports released another manuscript by me. Here primary human activity was related to the winter day. As an example, if you collect dinner times across Europe, you find sort of a chain reaction. They come from 6 p.m. in Sweden to 9 p.m. in Spain. However, unremarkably, they tend to be located some 3 hours past winter sunset. The main picture of the manuscript is a 2-layer composition. The first layer is the cycle of light and dark, upon which the second layer, the sleep-wake cycle, is to be placed. Here we have the winter setting. The left axis runs distance to the equator, latitude, but irrespective of the hemisphere. Axis spans from the equator to 55 degrees latitude, the latitude of Denmark and Patagonia. But notice that values are not equally spaced. Right axis is the winter photoperiod or daylight. It runs top to bottom and displays straight values. It spans from 7 hours per day to 12 hours per day. The bottom axis reads mean solar time. It's coupled to Earth's rotation. We have AM hours on the left and we have PM hours on the right. We have daylight or photoperiod in the lightest background. Here the sun is above the horizon. We have the night or the scotoperiod in the darkest background. Here the sun is below the horizon. Dotted lines display solar altitude. The sign of altitude is the efficiency of the insolation. They will be playing an interesting role. I will now identify 3 fundamental lines under gradients. They will be the synchronizers. First, noon occurs at 12, irrespective of latitude. Relative to the upright, we have no gradient. We can measure time relative to noon. Straight values of the photoperiod come handy because the line of umbra, the line dividing daylight and night, becomes polygonal and gradients have fairly straightforward values. Sunrise times have a gradient of -1/2. They decrease or advance with increase in photoperiod. We can measure time relative to sunrise. Sunset times have gradient of +1/2. They increase or delay with increase in photoperiod. And we can measure time relative to sunset. 1/2 means 1 hour of change in sunrise or sunset time per 2 hours change in the photoperiod. From the equator to 55 degrees latitude, sunrise delays some 2 hours, really a big deal. Now I'm gonna change this winter setting to the summer setting in the blink of an eye. The subsolar point made its way inside the canvas and the sun shines at 23.5 degrees latitude at the tropics. That changes almost everything. Sunrise and sunset reverse their gradients, and solar altitude at noon is much higher. Same happens from insolation efficiency, but more importantly, conditions at noon are fairly homogeneous in this range of latitudes and at this season. while in winter the gradient is evident. Now let's place human sleep timing above this layer. Here it is. Human sleep timing in the winter season. We have a sleep offset or wake-up times. They come close to the winter sunrise. We have a sleep onset or bed times. They come in the middle of the winter night. The midpoint is midways from wake-up times to bed times. Midpoints help to visualize that human sleep timing is not evenly disposed around noon, not even in pre-industrial subtropical societies. That is an important observation. Now, to see which mechanism best synchronizes human sleep timing, I let the synchronizers sweep the x-axis while recording how many data points are collected inside the band as a function of the position. Here are the results. The highest and narrowest peaks are obtained for distance to winter sunrise. Therefore, we have this scenario where distance to sunrise dominates human sleep timing in winter. The model of two processes of sleep regulation comes handy to describe these results. We have wake-up times regulated via photoreceptive circadian mechanisms, process C, which align them to sunrise. We get excited by natural light from the tropic to 55 degrees latitude. We have bed times regulated by a non-circadian homeostatic mechanism, process S. It is the mechanisms that make us feel tired after a long period of wake. Roughly speaking, wake-up times and bed times are separated by some 16 hours of wake or 8 hours of sleeping. Still, sunset plays a role in the discussion of bed times, which brings us back to the circadian process C, now shutting down human activity after nightfall. Pre-industrial bedtimes, especially those for societies without access to electricity, can be viewed 3 hours past winter sunset. Hard to say which process dominates because in the subtropic both of them coalesce. Say it is 3 hours after sunset, artificial light is poor and people decide it is bedtime. Or it is 16 hours after wake-up time, people will get up 8 hours later and people feel tired so they decide it is bedtime. Or a merger of these two decisions. As I already mentioned, in Europe at the extratropical range, dinner times happen some 3 hours past sunset within this photoreceptive box, and bedtimes of course come later as a result of later wake-up times. Bedtimes in Europe may have been once located at this photoreceptive being, but the being is more or less midways between two consecutive sunrises, and it is not that easy to keep 12 hours of continued sleep. Indeed, a period of wake at midnight, we call that segmented or biphasic sleep, is well documented in Europe in historical records. For sure, artificial light has impacted how human population living outside the tropics struggled with the wake in these exceedingly long winter nights. Human sleep timing delays with increase in latitude as a result of this setting. It is not a misalignment. It matches to the delay in winter sunrise times. It is the winter lag. Now consider the following argument. At the equator, wake-up times come 7 hours before noon at 5 a.m. This is too early for extratropical standards. However, people at the equator have all the outcomes for waking up by then. First, the sun is rising, but also they must take care of insolation at noon. It will be as large as 90% of the highest insolation on Earth. At the extratropical range, sunrise delays and noon insolation is not a threat. Therefore, the odds place towards delaying human activity in winter till sunrise occurs. The important question is, can this winter lag survive in summer? I'm gonna remove sleep timing and I'm gonna keep the lines. They will be still showing winter sleep timing. Then I will just bring this scenario to summer. Now it is all the way different. Even processes exchange roles. Bedtimes comes on 2 hours past sunset and we may say sleep is tied to the circadian process C. Wake-up times are tied to bedtimes by the non-circadian homeostatic process S. Wake-up comes after 8 hours of continued sleep or so. They will increasingly deviate from sunrise as latitude increases. Isn't that too late? Can this setting sustain? On the other side, keep wake-up times aligned to sunrise in summer also fails. Bedtimes now would come too early, before sunset, which is not welcome. So this setting is definitely too advanced, and this setting may be too delayed. Can we find a compromise? Indeed we can. Here is human sleep timing in summer. Can you track the difference with winter setting? Let's try with the binning analysis. Here are winter results with the narrowest peak on the left tied to winter sunrise. Here are summer's results. Do you see the difference? Now the narrowest highest peaks are obtained for the noon synchronizer in the middle panel. Now let's see what happened. Here we have human sleep timing in summer, while dashed lines still display the winter solution. You can see that the sleep timing in the extratropical region advanced relative to winter. And now the sun to noon is able to synchronize the sleep timing. In summer, the winter lag is all but mitigated. Irrespective of latitude, we have wake-up times at 5:30 solar time, believe it or not. We have bedtimes at 9:30 solar time, believe it or not. And we have midpoints at 1:30 solar time, believe it or not. This meridional synchronization should not be a surprise. With the subsolar point now midways from the equator to 47 degrees latitude, we have fairly homogeneous conditions at noon. The new setting comes to mitigate exposition and overheating at noon in the extratropical region, a behavior which is also found at the equator year-round. Still, there is one thing to put forward. Industrial societies have all become tied to clocks. Clocks are tied to noon, therefore they are non-seasonal. And people largely prefer year-round social timing, which would mean non-seasonal behavior. How do they shift from the winter setting to the summer setting? With the advent of the standard time some 100 years ago, that is accomplished by daylight saving time or summer times arrangements, the way in which non-seasonal clocks tick seasons. The spring forward brings the phase of the sleep-wake cycle 1 hour closer to the summer sunrise, and that mitigates the winter lag. The fallback resumes the winter setting. Inheriting the summer setting to the next winter season is also troublesome. I'm gonna remove again data points and I'm gonna keep the lines and just bring back this setting to winter. Now this setting, as I said, is troublesome and has not always been welcome. However, there is an ongoing preference for this setting in winter. It is a way of fighting against the winter lag, which means that it is influenced by latitude. For instance, a rationale is keeping distance to winter sunset in bounds. This is a concern at higher latitudes rather than at lower latitudes where the winter photoperiod is gentle. The problem with this setting is the transfer of wake under artificial light from the night to dawn. Quite certainly, artificial light can efficiently damp the relaxation mechanisms that occur after sunset. But artificial light does not work that efficiently at dawn. It is less able to bring alertness to humans. Sunlight does that much more efficiently. So this setting is irritating from the point of view of the circadian system. We largely tolerate wake after sunset and largely abhor wake before sunrise. You can learn more about the regulating role of daylight saving time at the extratropical range of latitudes in this comment letter recently published in the European Journal of Internal Medicine, and also in this YouTube video where I address this issue from a social point of view. Artificial light has doubtless impacted human life. However, no clues of misalignment have been found from this analysis. Human sleep timing still happens to be synchronized by natural events, and the golden standards, wake up by sunrise, bedtimes after sunset, are still preserved. This analysis is nonetheless based on averages. So please be wise, take care of your sleep timing, and take care of your daily sleep time. I do really hope you enjoyed this dissertation. It came to you thanks to these terrific pieces of software. Please have a nice rest of your day. See you soon.